there's a point A, there's a point B, and early on, even when we were developing the idea of the derivative, we were using this idea too, this idea of like the slope of the secant, right? So we're just sort of going to return to some of that conversation, but in context today. We have change in position, or the change in time. By the way, displacement is often delta s or something like that. So, okay. And then, again, all this should look familiar. I'm using, instead of h, I'm using a delta t to represent the change in the two positions over time. And we know that taking the limit of this quantity as delta t goes to 0 produces an instantaneous rate of change for us, if we like. Obviously, I think we've mentioned this before too, if you look down at your speedometer in your car though, it does give you an instantaneous velocity, so it's a concept we want to like maybe say something about, right? We want to make sure we are okay with that. And this is, are you okay, you like that with the delta t instead? Is that okay? DSDT, you want to call it? And of course, that's not just the average velocity, now we have the instantaneous velocity. So I don't know if have we said that yet? I think maybe we have, right? But in the context of this situation, we haven't had any situations yet that we've actually put meaning back on top of it yet, right? We've been practicing derivatives for a while now. We've done the formal definition. It's time to like return back to a context, and this is the most natural one to return to, at least for starters. And it should make sense that we get a function v of t, which is the instantaneous velocity with respect to time. Yes. T is the initial time. It's the time at the point of interest, right? So once you evaluate this limit, you'll get a function of t. So this v of t. It is actually a function of t when you're done. Yeah. Just like our formula f of x plus h, and with all that gives you in the end a function of x, right? So this is in general giving you the velocity, instantaneous velocity at any given time on your trajectory. So again, maybe a little bit of review, but in a new context, so that's not bad, right? Let's just say it like we mean it. Velocity is the first derivative of position. Okay, so that should be exciting. And there's a face. Okay. Speed we name to be the absolute value of velocity. Again, a thing that you've heard people say. Sometimes people say the magnitude of velocity is speed. So just in case someone asks you about speed, that's what we mean. Let's play around with an example. This is the free fall equation, and that's maybe I don't know, maybe Mr. McDonald or something. Okay, you know he's a skydiver. You know Mr. McDonald. Do you have Mr. McDonald? Yeah. He teaches AP Econ here. So he goes all the time actually. He's logged over 500 jumps. I think he told me. So he goes all the time. So this is, you might have remembered doing a little bit of projectile motion. We'll definitely return to ideas in projectile motion. You don't need to remember all of it to take this equation. It might look a little familiar, minus some of the other terms. For free fall, this is g, which if we're working in feet, which we will for this context right now, is 32. So here's a nice free fall equation, and by that I mean like this gives your position s above the ground at a time t, right? That's what this is. So we might ask, so there it is, simplified. In feet, this is measured in feet. So at position in feet above the ground at time t measured in seconds after you drop an object. And actually, it's actually not a great example to have these guys here because, yeah, because they're in that position especially, they have air resistance. So we're assuming no air resistance, unlike that picture over there. Okay, so they should be like, like this or something. And even then you have other discussions in physics to have too about terminal velocity and all that. We're not worried about that right now. Okay, so then what we're saying is, I trust that you can all take this derivative. What we're saying is that this is what's happening. Let's just make sure this, by the way, this actually makes sense. What is this actually saying? It's saying that like your velocity at time equals 0 is 0, isn't it? and that your velocity after 1 second is negative 32 feet per second, right? What's your position after 1 second? Yeah, and why all the negatives? What's going on there? Yeah, we're going down. So it should make sense that you're like by negative 16, by a position of negative 16 feet, we mean wherever you started, you're 16 feet below that now, and you're traveling after 1 second at 32 feet per second. That's your instantaneous velocity. So, and then you could try some other values besides 1 and get some other results. Wonderful. By the way, we'll say that on the next slide here. Yeah, someone already said it, but what is the next derivative we care about? Yeah, it's the change in velocity, right? So that's acceleration. We can say that more technically with our language, with our derivative language here. A is equal to dv dt. Or, said another way, the second derivative. Now here's our first use, actually, real world maybe use for a second derivative, for a higher order derivative. Maybe written that way in Leibniz notation. So that would be another way to say it. So in our example that we just did, what's the acceleration? It's negative 32, right? Just straight up negative 32. So what's your acceleration at t equals 1? And what's your acceleration at t equals 2? And 3, and so on. It's always negative 32 constantly. And this maybe already gives you some inclination for why, some insight into why the original equations look the way they did. It's because we want this to be the case. We want the acceleration due to gravity, the assumption that we're working with. In fact, the only assumption we're working with in these models is that we're subject to a constant acceleration due to gravity. And everything else just kind of gives rise to that, right? Now, going backwards is a thought process we haven't had to think about yet, but you can see maybe naturally how those came about. I don't know. So it makes sense that velocity should be negative 32t because we want the acceleration's the derivative to be a constant thing. We're always experiencing the same acceleration due to gravity. You're experiencing it right now. We're just used to it, right? Like if we should all be doing that all the time. I always like to say we should all be like if you experience 2 G's, that's what you would feel like. You'd be like, but if you're used to feeling 1 G, so you're like, it's natural. You know, you're not always like freaking out. But you know what? Exactly right. So now insert like health discussion or something. Yeah. What would you like to, maybe right, what would you like to call it? Would you like, D? Can you see why already, why D might be an issue? Y is not bad. D might be a little bit of an issue. Y would be okay. Y would be okay. H in this context would be okay too, since in this particular context we're talking about like vertical displacement. So yeah, and we'll use some of those other letters too. Absolutely. What are the units? Let's just say what that is. I think we've maybe said it out loud, but let's actually. Yeah, so acceleration is, and this, we need to make sense of this. I think a lot of people in physics class, like, when they hear the acceleration, that negative 32 is in feet per second squared, they're like, okay, let's just go on and move on. But why does that make sense? Give me a couple of different perspectives of why that makes sense. Raphael, yeah. Okay, why does that make sense? Yes, I agree. Yeah, why does feet per second make sense? I agree. In fact, feet per second squared is not helpful. We should maybe always say feet per second. You want to keep going? All right, and then we got other people in the wings too. Yeah. Is that what you were going to say?
Yeah, you keep the roots made up.
Okay. Does it make sense to, I mean, some people still even struggle there with two time units, but it makes actually good sense. In fact, could we make sense of units like miles per hour per second? Does that make sense? Sure. Like if you are in your car and you're traveling at a velocity of, 40 miles per hour, and then you want to accelerate at 2 miles per hour per second, that makes good sense. Over the course of 3 seconds, then your velocity will be 46 miles per hour, won't it? And if you accelerate 2 miles per hour each second, of course it makes sense to have two time units in there. I was traveling at 40 miles per hour, and 3 seconds later, if I accelerate at 2 miles per hour per second, then 3 seconds later I'll be at 46 miles per hour, right? Just this. All right, so it should make good sense why you have two time units in there. So I'll put up the things people just said. Of course, those units could be different depending on the problem. We might be working in miles per hour. We might be working in meters for whatever. So furlongs per day, whatever. Something could be any distance divided by time would do. By the way, just because there are physics nerds in the room, what are the next derivatives called? They actually give names to them. The third derivative, you know the name? I just figure there's someone in the room that knows this, but maybe not. The third derivative is actually something you do care about if you're like designing cars or roller coasters or something like that. It's called jerk. It's the change in acceleration. You want that to be at a minimum. Yeah. And then the next three derivatives are called snap, crackle, and pop because physicists are like think they're funny. I can't give like a jerk actually makes sense. The third derivative actually still makes sense to me, like physically. I feel that. I understand. Like if you accelerate non-linearly in your car or decelerate, maybe like you have a parent who does that or something. You're like, then you can feel the third derivative. I'm not sure I understand like from a physical perspective what the next derivatives mean, but we maybe care about those too. So. Graphically, we have some pictures to think about too. Let's look at a DT graph and think about. Also, looking at DT graph, let's think about what's happening with the velocity and acceleration at all different points on here. Let me highlight a couple different intervals here. So this first interval, I'm thinking on this interval right here, up to that point only. Tell me what's going on with the velocity. Yeah, we have both, right? The velocity is positive, and the acceleration is positive also, right? You see that? How that affects the graph? Right, so we're talking about like two derivatives worth of information there, okay? So the acceleration is positive, and the velocity is positive. And what's the distance doing? Well, it's increasing, right? So we could talk about all three things here at once. And if you're like, and actually tomorrow I'll bring in a motion sensor and we'll play around with it. But if I had a motion sensor that was giving you the distance of me away from it, tomorrow I'll bring one and I'll set it here. And I were to, what would this look like? What would this look like? Well, it would look like this, right? I'm moving away. My velocity is positive, and it's also getting bigger. Like I'm actually ramping up my speed. Okay, what about the next piece there? And let's assume that's linear, say. It's just like a perfect line for the sake of discussion. I don't know that it would be. But. So there, the acceleration would be 0. Velocity is constant-ish, yeah? And distance is still increasing, right? So so that would be us. Let's see if we can model this, right? You're like ramping up and then you're like nice steady pace, right? Okay. What about the next piece there, up to the peak? What's going on there? Someone else I haven't heard from. Here, let me call on someone. See how you're doing here. What do you think? What do you think is going on? Can you describe all three things? I've already heard from you. No. Where's Grace? Talk to me about this one when you're ready. Can you talk to me about what's going on that piece? Okay. Yeah, we want to be careful about what we say is decreasing. I think I know what you mean. What is decreasing? Okay. Decelerating. Okay. If we're talking, acceleration captures that already, though. So what is changing, though? Well, I mean, what's the? Yeah, the velocity is decreasing, right? If you're looking to fill in the blank, what is decreasing? It's the velocity that's decreasing. Yeah, absolutely. What's increasing? On that interval. There is something increasing. What's that? yeah, the distance is still, your distance away is still increasing, right? So the velocity is positive. That's still true, but so now we're like slowing down. So let's see if I can like do the whole thing, right? Accelerate, nice even pace, and then now, what happens right at the top here? Oh. Nobody knows. Yeah, that's where I have the zero velocity, right? And then what's about to happen? Well, we'll have to look here. What about this next piece? Jonathan, you have something to say?
The next piece?
Oh, yeah, you want to take it? Go for it.
I think the acceleration.
Again, be careful with your words. You're going to criticize the way you said that in the same way I just criticized Grace's way of saying it.
So velocity increasing again?
Uh,
Are we moving backwards?
Well, yeah, what do you think? Let's talk about distance first before we talk about the other things. What's going on with the distance?
It's going down.
It's going down. So, yeah, what am I actually doing if you're giving me instructions? I'm actually like starting to back up now, right? What else do you want to say there? Yeah, so what about velocity?
Velocity is
Yeah, but backwards, so what do you call that when it's only increases but backwards? You might call it decreasing, right? Or isn't the velocity actually getting more negative? I mean, keep in mind what velocity means. I think you're losing sight of what velocity means. It means the slope of the graph. So the slope here, as we go here, is increasing, and then the slope is constant, and then the slope is decreasing, and by slope here we mean velocity. So what's it doing here? Well, I mean, there's a sense in which it's increasing, but I think what you mean, what's increasing there? About the speed is increasing, but the velocity is still decreasing. Like, let's just start calculating the slopes in your mind, right? Here it's 0, 1, 2, 3, constant, 3, 3, 3, 3, 3, oh, down to 2, 1, 0, negative 1, negative 2, negative, it's decreasing, isn't it? I mean, I know it feels like that's a weird thing to say because it's getting kind of steeper, right? But you're thinking about speed there, yeah. Anyway. So the acceleration is negative still. The velocity is negative, and it's decreasing. What about the next piece there? Again, assume that's constant. The velocity there, the slope of that line is constant. So what do we want to say there? How about Peter? You want to take that one? What would you say on that interval? Describe my motion here. Give me instructions. Which way am I going?
You're going back.
Yeah, okay, I'm going backwards, kind of. Yep.
Velocity is negative.
Right?
And acceleration is 0.
Exactly. So now I'm in the same kind of way that we were earlier. I'm now reached a steady pace, nice even constant velocity headed back toward the motion sensor or whatever. Okay, perfect. And then, so the acceleration is 0. If in fact that's a line, then acceleration is 0. The velocity is negative and constant. And the distance is decreasing, if you want to say it that way. And then on the last piece here, what do we want to hear from Ian? Take it away. Yeah, it's weird to see that graph and say anything about that is increasing, but okay, keep going.
And acceleration is decreasing, or
It's hard to know what I mean. It's definitely acceleration could even be constant here, but but the velocity you just said is increasing, so the acceleration is positive, right? I don't know whether it's changing or not necessarily, but I do know that the acceleration is positive based on the shape of that graph. So again, this seems weird that acceleration would be positive. What about that is positive? Or to say anything about this graph is increasing. But again, if you think about the slopes, where were we? We're pretending this was like a slope of 3 or something like that. That is, the velocity is 3 all along here. Excuse me, negative 3. And then now it's what's going on here. As soon as we hit this point, we're going back up to negative 2, negative 1, 0. That is that. You're right, Mr. Chase. That is the velocity increasing. It's a little weird. Because again, the speed is headed toward 0, so you know you think you're slowing down. You are slowing down, but your velocity is actually getting more positive, isn't it? Right? It's getting closer to 0. That's us getting more. That's us increasing. The velocity is increasing. So, and now I'm back home at the motion sensor. All right. And then imagine if this were to level off, then of course acceleration and velocity would both be 0. So thank you for working that through with me. Let's talk about this volcano. All right. Are you ready? Okay, historical facts. This is actually taken from somewhere that's actually true, 1959. How do we say that? Iki. How would you say that? Any Hawaiians? Iki erupted in Hawaii. Okay. And at one point, the lava was 1,900 feet straight in the air. Some particle of lava, apparently, was measured to go that high. Wow. Using this position equation, I'll just give that to you as a free gift from me to you, where V0 represents the initial velocity. Tell me what that initial velocity was. How fast is that stuff coming out of there? It seems like not much information to go on. In fact, the only number I gave you besides the useless 1959 is 1,900 feet. So like really the only useful piece of information I gave you. And from that, can we deduce all the rest of the things we would like to know? Well, let's just like kind of play our game of what do we know. Right? We were given a position function, that is the displacement vertically above the open mouth of the volcano. The velocity equation we can derive in terms of this constant. This is kind of like the homework last night where you have to take a derivative here. I'm taking a derivative here, realizing that V0 is a constant. So that's not part of the differentiation. It's just as if you were taking the derivative of like, 15t minus 16t squared. Right? It works the same way. V0 just kind of comes along for the ride. So there we go. We got a velocity equation. That's wonderful. Okay, so I'm ready to to say something about the 1,900 feet. Like, what do we know about that point besides the fact that it's 1,900 feet at one point? Is there anything useful we can say, Katie? It's the maximum. Anything else we can say? Becca?
At the maximum, it'll be slope of 0.
Yeah, which means in particular this equation takes on a value of 0 at that point, at the maximum place. So that's good. That gives us a relationship between V0 and T, which we like. Still doesn't solve the problem for me, but that's useful. I think that's really useful to notice, is that at the point of interest, this point right here, the height at that moment, whatever that was, the velocity was 0. So let's return to the position function. And if this is the case, that at the time when it peaks, that t value has this property that is equal to the initial velocity divided by 32, then I think, where are we going to go from here? Yeah, we're going to plug it in. And what else can we plug in? Because that's still maybe not enough. I'm going to plug in V0 over 32 for t. And what else? Yeah.
Plug in V0 into over 32 into t.
Right. What about so we'll have a V0 in there. But we'll still have this S, won't we? Like we'd love an equation that has V0 in it. Only, because isn't the task of this problem to find V0 basically? Right, isn't that what we're asked to do? So what other move am I going to have to make there? We haven't used another. Charlotte?
Can you put the 1,900 into that?
Yeah, isn't that, that was like the conversation we had just a minute ago. Isn't that going to be the height? When we have this particular time where we have a maximum, whatever that maximum height is, we should get a height of 1,900 at that time. So I think we can figure out what V0 is. Do the work. That's a 32 squared in the denominator. Multiply by some stuff, divide by some stuff, take a square root, use a calculator. Okay. So, you all right?
Yeah.
So that's fast, 348.7 feet per second. Oh, this is a good opportunity, by the way, I'm being your example here, to tell you that in AP, the rounding, I don't feel like we've had to round very much yet in life, but AP rounding is 3 decimal places.
What?
Is that gonna mess you up?
That's stupid. Why not something?
It's always 3 decimal places. So there you go. And they also allow you to either truncate or round at the last decimal place. So, okay.
What if it's like a really
I think it's actually better than the IB sig fig rule a little bit, because the IB sig fig rule is completely arbitrary to the context.
But what
So
if it's like a really small number? Like
the
you
very
just know-
best rule would be like what you actually do in science class, and that's like to actually like think about the sig figs that you might have measured and like let that carry through your calculations in a meaningful way. But so that's a good example. Three decimal places, please. All right, let's practice some of these concepts on this handout, which is coming to you now.
I guess so.
Yeah, yeah.
Actually, never mind. Sorry, no, I know I cut you off there. What were you gonna say? A while ago, right? Yeah. You're gonna get a dot play.
You guys have probably seen this toy on my desk if you've never played with it, right? You've seen this. So I think about that, the fact that the velocity is 0 every time I play or with this, or if I teach someone to use this. The best time to like catch this is right as it's peaking, right? Because if you're catching it as it's like flying down, then it's moving quickly. But if you catch it at its peak, then its velocity is approximately 0, right? So like you want to like catch it right as it peaks, right? Because then you have like your whole world slows down, like mind like water, right? So that's the idea. It's a little harder to catch it elsewhere, but right at the peak is where you want to catch it. Right? So come play with this sometime.
Quick tricks, Mr. Shea.
Maybe.
Just one. One trick.
You know I'm a sucker. I just did show you a trick.
Quick tricks are a good one.
That's the thing, it's just fun with it.
I know. All right, I'll go around the
Rather what we got.
So this is called Around the World. Small cup, big cup, little cup, spike. This is called, that was the warm up. This is called Around the Universe. Bounce on the cross and slide the spike. Small cup, spike, big cup, spike, base cup, spike.
Are you
I was talking about velocity being 0.
Really? You're supposed to be teaching, not playing. Or if he's going to do that, you demand that he's on his unicycle at the same time.
It was right. It was awesome. Get in trouble.
That was awful.
It was awful every time I saw that.
Did she drop a point? No, you get this every time.
Yeah.
If you have 3 colors in your arsenal, you might graph these 3 functions on this grid in the 3 different colors you have. Does anyone have 3 colors?
Honestly, all I have is
Some of you are having trouble maybe just with the algebra 1 skill of graphing that parabola, right? I think it factors nicely, doesn't it?
It does.
So that would help you find the 2 zeros at least. You know the y-intercept right away too, don't you? So that's 3 points right away you have on the graph. 4 points if you use the symmetry, right? it, you know, negatively over 2. I mean, now we can prove that now. Well, no judgment like that. That's a little harsh.
4 minus 8. 4 plus 1 is 7.
So we have from 0, 3, 1, 0, 3,
So I would like you to continue working on this here. You have a few minutes. Can I just pause and ask you one thing on the back though? No, it's not on there. I do want to ask you something. I feel like it's going to come up in the homework maybe. But I'd like to ask you this. How do we know when a particle or a thing is speeding up or slowing down? That's a piece of language we'd like to use. We've already used it a little bit today. But let's formalize that. How do we know when something is speeding up or slowing down? Yeah. Yeah, so if the speed, if the velocity is positive and the acceleration is negative, that means that you're going this way, but you're doing so more slowly all the time, right? Your acceleration is negative. There's another case too when you'd be slowing down. When would that be? Your velocity could be positive and your acceleration be negative. Or, if you're going this way, your velocity is negative and your acceleration is positive, right? The point is the velocity and acceleration are opposite signs, right? That means you're slowing down. And when are you speeding up? When is your speed, the magnitude of your velocity increasing? When they have the same sign, either both positive or both negative. So that's something that I think will come up a little bit in the homework. I just want to make sure you're prepared for that moment in your life. The homework is homework 5. Homework 6, excuse me, from the left. But if you have to finish this, then finish this too. Just for fun. Right. It's for homework. For you. You could finish this like today, right now. It's really not. It's really not a lot to say. Yeah, homework 5.
Please pardon this interruption. This is a reminder to all freshman students attending Unity Day tomorrow. Please check the weather and dress appropriately. This event will go on as scheduled, rain or shine. Also, any black masters doing set construction, there will be no set construction today. See you all tomorrow. Thank you.
I nominate what I can do first semester. And then second semester. Like, if it's a group, I would rather just do it myself. Exactly.
I think this is, I don't think this is,
I'll offer that for myself. I want to like break a friendship.
where's Kathy? Bye. Anyone else out tomorrow? Yeah. Anybody else out tomorrow? Any reason?